We look up at the night sky, and it's so easy to think of stars as these eternal, unchanging little pinpricks of light. But they're really not. They are actually raging, dynamic furnaces with incredibly dramatic lifespans. Today, we're diving straight into this explainer to look at the mind-bending physics that dictate exactly how stars eventually die. It's a story of absolutely colossal proportions happening right over our heads, and it all comes down to an invisible, high-stakes war waged deep inside the stellar core.
So here's the big question. When a star finally exhausts its nuclear fuel, when that internal fire literally just goes out, what happens next? Why do some stars kind of just quietly fade away into these dense, peaceful little objects called white dwarfs, while others go out in the most violent, spectacular explosions in the universe? We're going to investigate these two wildly different cosmic fates and figure out the exact mechanics that force a star down one path or the completely opposite other.
First up, consider the sheer calmness of a white dwarf. This is essentially our first crime scene in this cosmic mystery. It seems so serene, right? Just a quiet remnant glowing softly in the vastness of space. But honestly, do not let that peaceful vibe fool you for a second. A white dwarf is incredibly dense. To put that into perspective, if you took just a single teaspoon of this material, it would weigh a full ton here on Earth. It's basically a tightly packed graveyard of a star that's totally finished with nuclear fusion. It's stable. It's silent. But to understand how a star can even end up like this, so compact and quiet, we really need to zoom out and look at the whole shebang, a star's entire life cycle.
Because the paths a star can take are vastly divergent. An average, low-mass star, kind of like our sun, starts out in a stellar nebula, swells up into a red giant, gracefully sheds its outer layers, and then just leaves behind that quiet white dwarf we were just talking about. But a massive star? Oh, that's a completely different story. It swells into this absolutely monstrous red supergiant, and when its time is up, it doesn't just quietly fade away. No, it detonates in a terrifying supernova, leaving behind either a neutron star or even a black hole. The roadmap is clear. But why does the road fork so dramatically based just on the star's starting size? Well, the answer boils down to a fundamental conflict. You really have to think of a star's entire existence as a high-stakes, billions of years-long cosmic tug-of-war. Literally every single second of a star's life is defined by this relentless battle between massive, macrocosmic forces and tiny, micro-subatomic rules. And whoever wins this tug-of-war, that completely dictates the final fate of the star. Let's break down the teams. On one side, relentlessly pulling inward, we have gravity. The immense mass of the star is constantly trying to crush itself down into a single point. Now, while a star is alive and burning fuel, the heat creates this outward pressure to balance out that crush. But when the fuel runs out, gravity starts winning. The core begins to collapse. And just as it gets incredibly, unbelievably dense, the ultimate defender steps into the ring to push back. Electron degeneracy pressure. This is a microscopic outward push that fiercely resists that crushing inward weight of gravity. To really wrap our heads around where this incredible outward push actually comes from, we gotta crack open the quantum rulebook. It all hinges on a physics concept called the Pauli exclusion principle. It's a fundamental law of quantum mechanics that simply says you cannot have electrons occupying the exact same quantum state at the same time. Think of it like trying to cram way too many people into a tiny elevator. Eventually, someone's going to throw an elbow, right? They push back. So as gravity squeezes that dead star's core tighter and tighter, these electrons stubbornly refuse to be squished into the exact same space. That refusal creates that immense outward force we call electron degeneracy pressure. This quantum pressure is so powerful, it works even at freezing temperatures, and it's exactly what holds up a white dwarf, keeping it perfectly stable against its own gravity. But that brings us to a pretty terrifying yet brilliant turning point in our explainer. Because yes, this quantum pressure from the electrons is incredibly strong. But is it invincible? Like, what if gravity just gets too strong? What if the mass of the collapsing star is simply so enormous that this microscopic outward push is no longer enough to hold the line? Ultimately, what happens when that quantum wall breaks? To answer that, we actually have to look at one of the greatest scientific underdog stories of the 20th century. Picture this. It's 1930.
A 19-year-old Indian physicist named Subramanian Chandrasekhar is traveling by ship from India to England. He's literally just a teenager on a boat, and to pass the time on this long voyage, he decides, just for fun, to apply the complex rules of quantum mechanics and Einstein's special relativity to the cores of dying stars. Through his math, he discovers the exact maximum mass that electron degeneracy pressure could possibly support, which is roughly 1.4 times the mass of our sun. Now, for decades, his revolutionary idea was strongly opposed by the scientific establishment, especially by the famous astronomer Arthur Eddington. But, as we know, science eventually catches up with the truth. Decades later, observations proved that the young Chandrasekhar was absolutely right all along, and he rightfully took home the 1983 Nobel Prize in Physics for this astonishing discovery. The absolute crucial point here is this universe-altering revelation. A white dwarf cannot have an unlimited mass. There is a hard mathematical ceiling to how much weight those stubborn little electrons can actually support. Chandrasekhar proved beyond a shadow of a doubt that if a dying star's core exceeds that 1.4 solar mass limit, the inward crush of gravity becomes overwhelmingly stronger than the outward electron degeneracy pressure. Basically, the electrons give up, the core collapses further, and the star absolutely cannot remain a quiet white dwarf. And when gravity finally wins that cosmic tug of war, well, things get intense. When Chandrasekhar's mass limit is exceeded and the core collapses past the breaking point, it triggers a cataclysmic shockwave. The star detonates in a wildly violent supernova, an explosion so incredibly bright it can literally outshine its entire home galaxy. What's left behind is no longer a quiet, stable remnant, but something far more extreme born straight from the fires of that explosion, an ultra-dense neutron star, or, if the core's mass is great enough, a black hole. So this beautifully resolves our initial mystery. The contrasting fates of stars, they aren't random at all. They are entirely dictated by this delicate, high-stakes balance of forces. The ultimate mass of a star dictates its gravitational pull, and that gravity decides whether it can peacefully rest on a bed of quantum pressure as a white dwarf, or if its sheer weight will shatter the quantum wall, crushing itself into a spectacular supernova. The brilliant mathematical limit calculated by a 19-year-old perfectly explains the destiny of some of the absolute largest objects in our universe.
Which really leaves us with one final, pretty provocative thought. If a teenager on a boat in 1930 could use just his understanding of physics and mathematics to uncover the explosive fate of massive stars across the entire cosmos, what else is out there? What other profound, universe-altering secrets, hidden right in the balance of invisible forces, are just waiting to be solved by the next generation of curious minds? Keep looking up, keep asking those big questions, and we'll catch you in the next explainer.